Good day and welcome to another slide video from the Cornish Radio Amateur Club, and this is in the Foundation series for the RSGB Foundation exam. And today we're going to be looking at units and multipliers. Now for the Foundation we only need to understand the basics, so we have looked in video 3A at basic symbols and diagrams, and this is 3B looking at multipliers, milli, kilo and mega. And let's have a look at the syllabus, because we're going to expand this requirement also to look at units. So let's have a look at the technical basics. The technical basics part of the syllabus says units of measurement and multiple submultiple prefixes. And if we look at what's under that, this is the only item we have to cover. 3A1, identify the units of and abbreviations for potential difference, brackets voltage, current, power and resistance. And it says note, prefixes milli, kilo and mega may be used. Now we're going to go on a little bit further than that, because in other syllabus items we have to have a look at some other units as well. So this now is, we're going to look at now all of the units that we need to understand. Now the first unit, a fairly easy one, I think we're all familiar with it, the unit of length, the meter, and its abbreviation, lowercase or small m. We need to look at the unit of time, second, lowercase or small s is its abbreviation. The ampere, which we may not be familiar with, often called the amp, and that's the unit of current, and that's how many electrons or charged particles flow past a given point in 1 second. So I think most of us will be familiar with fuses, and if you have a look at the video on symbols for the foundation course, that may give you some insight into the amp. Certainly we will be covering it in later videos when we look at Ohm's law. So the ampere with a capital A is the abbreviation. The volt measures potential difference, and that's a capital V. The unit of resistance is the ohm with the Greek symbol omega. Looks like a horseshoe. Watt, capital W, measures power. And then finally the Hertz, HZ, measures frequency. Now the three in blue are the base units, and the three in brown are derived units. We don't need to know that because that is more than is required by the syllabus. Indeed, more than is required by the advanced syllabus. It comes into the story of the SI units, the System International units, and there is a background video on SI units if you need to understand this in more detail. But I've just put it there for interest. So when you look at the abbreviations, you notice that some of them are capitalized and some of them are lowercase. The rule is with abbreviations that if it's somebody's name, it's a capital, and if it's something that's just grown up historically, like the second or the meter, it's lowercase. And it's important to distinguish between that. So ampere, volt, ohm, watt and hertz were all people, and you can Wikipedia those to find out how they contributed to their field, but otherwise just remember that if it's somebody's name, it's a capital letter. Let's have a look then at voltage, current and resistance, and we'll look at the Hertz in a subsequent slide. Now voltage resistance and power. Let's have a look at that. In the symbols video, we had this graphic here, and we show that voltage is driving the current around a circuit, and resistance is opposing the current. So the animation of the graphic shows that the voltage pushing the current around the circuit and the resistance trying to constrain the current from flowing around the circuit. So we say that the voltage drives the current around the circuit and resistance is the opposition to current flow. And the act of current going through a resistance causes heat. It causes power to be dissipated, and you can see then the power dissipated as heat on the little thermometer there. So this is a useful graphic to kind of remember when we go through the explanations that follow. Let's have a look at Hertz frequency. Here we have our transistor radio, and the Hertz is inextricably linked to the second, one of the other units that we have to understand. So here, if we stick up the aerial on the antenna, we'll have all frequencies arriving at the aerial, and a tuned circuit within the transistor radio will select the station that we want to listen to. So here we're tuned to a lower frequency signal, and you can see we haven't got very many oscillations, if you like, happening. And as we tune up on our dial, we get to a higher frequency. If we tune back down again, we go to a lower frequency. And that's a good image to keep in your mind as you go through the course. If we change the color of each one of the cycles to distinguish between them, we can see that one cycle starts at 0, goes fully positive, back through 0 to fully negative, and back to 0. And that is what we call one cycle. That's one cycle of the electromagnetic radiation that's carrying the music or speech that we're listening to. And it's important to remember that transition fully positive, fully negative, and back to 0 is the cycle. It's a very common mistake to interpret a half cycle as being a cycle. In other words, from the 0 fully positive and back to 0. That isn't a cycle. A cycle goes fully positive and fully negative and back to 0. So here then, if we count the number of cycles that we have in the 1 second, you can see that we have 1, 2, 3, 4, 5. So we can say our frequency then is 5 cycles per second. Now, cycles per second is the old historic way of measuring frequency. Indeed, if you look on some antique radios, on their dials, you can see CPS marked on the dial, meaning cycles per second. But under the SI system, cycles per second have been renamed to Hertz. So here we have the frequency equals 5 cycles per second equals 5 Hertz. And there's the abbreviation for Hertz, a capital H and a small z. A capital H because it's the person's name. Now, if we have a look at the last cycle there, the one that's pulsing there on the screen, we can see then the duration of just that one cycle is 1/5 of a second. I can say that because there are 5 cycles in 1 second, so each cycle must be 1/5 of a second. And we call that the period. The period of one cycle, in this case, is 1/5 of a second, and the abbreviation for that is a capital T. So we can say T equals 1/5 of a second. Once again, you don't need to know that for the foundation course, but you will start to need to know that for the intermediate and definitely for the advanced course. So it's a good point to illustrate that, but not necessarily not necessary for you to memorize. Now, here we have a frequency into this radio of 5 cycles per second. Well, you'd be quite right to say, well, I've never heard of a frequency of 5 cycles per second being used for radio communication. And if it were, it would be ELF, extremely low frequency. But I've never heard of it happening either. The lowest I've heard of is communication to American submarines at 76 Hertz, which was very, very difficult to achieve, excuse me, and required antennas that were 23 kilometers long. The only reason they did this is that it allowed them to communicate to their submarines while they were still underwater, because frequencies at ELF do penetrate below water, whereas high frequencies do not. Now, if we have a look at some more common frequencies, ones that we might actually encounter, here we have our transistor radio, and there's a dial, and they're currently tuned to the bottom end of the MF band, sometimes called the medium wave band, at 530 kilohertz. You can see the small k, HZ, capital HZ, kilohertz, written there on the dial. So it's tuned to 530 kilohertz. If we tune up in frequency to 774 kilohertz, we would probably hear BBC Radio 4 transmitter, which is transmitting from Plymouth on 774 kilohertz. How would we change 774 kilohertz back into the base or derived units, the derived units of Hertz? Now, I like to call the base or derived units the fundamental units, if you like. That's a unit without any multiplier attached to it. So how do we get from 774 kilohertz to Hertz? Well, we can rewrite 774 kilohertz as 774.0000 and as many zeros as we like, because that doesn't change the value. This is just a convenience method of doing it, if you like. We can take the decimal point then, and because it's kilohertz, an easy way to multiply by 1,000 is to hop 1, 2, 3 places to the right. And once we've done that, we can rewrite it then as 774,000 Hertz, 774,000 Hertz. And that is a more realistic frequency to tune to than the 5 Hertz that I used illustratively in previous slides. So you're getting the idea here that kilo is a multiplier. Let's look at all of the multipliers in the SI system. And here they all are. Now these, well actually not all the multipliers in the SI system, these are all of the ones you need to cover for the foundation, intermediate and advanced level. So if you knew all of these, you'd be good up to advanced level. But for the foundation course, we only need to know mega, kilo and milli. If you recall that, that was specified in the syllabus, which we went through in the second or third slide. So here they are in green. Mega means times 1,000. Kilo means, I beg your pardon, mega means times 1,000,000. Kilo means times 1,000. And milli means divided by 1,000. Now a common mistake, because milli sounds like million, is to think milli is divided by a million. It is not. It is divided by 1,000. And an easy way to remember this is millimeter. mm, small m, small m. Small m because the symbol for milli is a small m, and the second small m because the symbol for meter is also a small m. And millimeter, you should know, if you look at a meter rule, there are 1,000 millimeters in a meter. So getting rid of the extraneous multipliers, here they are again. Mega times 1 million, kilo times 1000, and milli divide by 1000. So let's have a look at some everyday examples. And here we won't use any electrical symbols, we'll simply use some speed equals distance over time calculations, ones that we do every day when we're figuring out how fast we're driving. So let's have a look at a car travels 2.5 kilometers in 3 minutes and 20 seconds. What is its speed in meters per second? Again, you see the small m for meters and the small s for seconds. There's a car on the road, and there's a stopwatch, and it's travelled 2.5 kilometers in 3 meters and 20 seconds. So, remembering that speed equals distance over time, it would equal to 2,500 meters, that's 2.5 kilometers, expressed in base units or fundamental units, divided by 200. Why 200? Well, 3 minutes and 20 seconds, 360s are 180 plus 20 seconds makes it 200 seconds. So the answer is 2,500 over 200, and if you put that in your calculator, you should have 12.5 meters per second. That's the average speed of a car over that distance given that time. And we've gone back to the fundamental units of meters and seconds. Now, how did we do that? Let's have another look at it again. Still the same calculation. Looking at that 2.5 kilometers there. We can write it as 2.5 and as many zeros as we like afterwards. That doesn't change anything. And simply we go 1, 2, 3 hops to the right, and 2.5 kilometers becomes 2,500 meters. And so we can correctly write it as 2500.00 m, small m for meters. We don't have to do the decimal point or the last 2 zeros, but that's it doesn't change anything. It's just a matter of presentation. Let's look at that decimal point hopping for the same example again. 2.5 kilometers is 2.5, 0, 0, 0, 0. We go 1, 2, 3, and then change units from km to m equals 2,500 meters. Let's have a look at another one. Here we have a snail travels at 300 meters in 100 seconds. How fast is it traveling in meters per second? And there's the snail traveling, we measure it with a ruler. So, speed equals distance over time, and we can write it like this, 300 mm, that's okay, over the time, which was 100. But we need to get back to base units. We need to express the answer in meters per second. So that would be 0.3 meters over 100 seconds, and that would be 0.003 meters per second. Let's look at the decimal point hopping for this example. 300 millimeters is equal to 300 point something something something, or 0.000. But here we need to go from millimeters to meters, so we decimal point hop, but we hop in the opposite direction. We hop to get a smaller number, and that means hopping to the left, and that gives us 0.3 meters. Now, if you can do successful decimal point hopping for millimeters to meters and meters to millimeters, then there's no reason why you can't use the same technique for things like Hertz or volts, etc. But distance is a useful yardstick, if you'll excuse the pun, because we all know that there are 1,000 meters in a kilometer, and we know that there are 1,000 millimeters in a meter, etc. So, for example, then we know that there are 1,000 volts in a kilovolt, or 1,000 ohms in a kilo ohm. So then here's a reminder then of the whole list of the multipliers, and you may wish to learn them all. Why not? It's a good opportunity. But for the foundation level, we only need to look at these three. Mega times a million, kilo times 1,000, and milli divided by 1,000. So why do we use multipliers if we seem to spend such a lot of time converting between fundamental units and the multiplier equivalents? Well, the numbers that we have to deal with are often very large or very small, and we need an easy way to express these numbers both verbally and mathematically. This is particularly the case with frequencies. If you wanted to say, I don't know, 1.5 gigahertz, it would be very difficult to express this verbally as 1,000,000 1.5 gigahertz would be 1,500,000,000 hertz. You can see the difficulty here in expressing it, but 1.5 gigahertz is easy to express. 2 megahertz, it would be difficult to say 2 million hertz, or more difficult to express it that way. So multipliers are now in common parlance, and we need to be able to comfortably move between the various multipliers and the base or derived units. So let's have a look again then at the units and multipliers. This is just going over what we've done. Here are the units: the meter, the second, the ampere, the volt, the ohm, the watt, and the hertz. You need to be able to recognize, because it is a multiple choice, but I would suggest be able to write down the abbreviations, and be careful here that you get the capitalization correct. That is important. And here are the three multipliers that you need to be able to remember. Let's do some examples of these now. Let's have a look at seconds. 2 milliseconds. How would that be in seconds? Using the decimal point hopping, you should come up with the answer 0.002 seconds. How have we done this? We've written 2 milliseconds as 2.0 milliseconds, and we've hopped 3 places to the left. We can use padding zeros in front of the 2 milliseconds if that helps. You can write 2 milliseconds as 0.00002 milliseconds, and that gives you a place to hop the decimal point into. Similarly, 5 milliamps would be 0.005 amps. Note the milliamp there, the small m for the milli, and the large A for the amp. By the way, if you look at all of the multipliers, all of the ones above 1, apart from kilo for historical reasons, are capital, and all of the ones less than 1, or below unity, are small letters. So they follow a rule: anything bigger than 1 is a capital letter except kilo, and everything smaller than 1 is a small letter. So 1.2 kilovolt, small k, capital V, because it's after Mr. Volta. So 1.2 kilovolt. In volts, I hop 3 places to the right, so it becomes 1,200 volts. 20 mega ohms becomes 20 million ohms, because this time I have to hop 6 places to the right. So I start off by writing 20 mega ohms as 20.00000, etc. ohms, and I hop my decimal place 1, 2, 3, 4, 5, 6, and I will end up with 20 million ohms. Notice the capital M for mega in mega ohms. 0.6 milliwatts. Again, this time I'm hopping to the left, so I put some leading zeros in on the left, and I hop 3 places. So my 0.6 becomes 0.0006 watts. Let's go the other way. Up till now, we've always taken multiplied units and gone back to the base units. Let's take a base unit and go to a convenient multiplied unit. Let's take 400 million Hertz, and then see, well, what would that be conveniently expressed as? Well, 400 megahertz would be good. This time we've divided by 1 million to get megahertz. So 400 million hertz is 400 megahertz. So have a practice with these. If you are only going to do the foundation exam, then it probably isn't worth spending too much time on. It'll only yield you a few marks, maybe a couple at most. But if you're going to go on to do the intermediate and the advanced, practice with units and multipliers is never wasted, because it will come up time and time again in some of the calculations that you will need to perform later on as you progress through the levels. So there are the units, there are the multipliers that you need for the foundation exam, and thank you very much for listening. Next we will be looking at video 3C at conductors, conductors and insulators.